Hello, I am Professor S. Shankaran in the Department of Metallurgical and Materials Engineering.
So now we'll move to the dislocation, dissociation, that is partial dislocation, especially in FCC crystal. Why just in FCC crystal? Because in other crystal forms, these partial dislocations are not that stable. It is not that it is not able to form or something like that. In FCC crystals, it forms, it remains stable. So please understand. So most of the textbook talks about FCC partial dislocations. It is not that it is not forming in VCC, other crystal forms, they may not be stable. In FCC crystals, slip occurs on 111 planes and in 110 directions. Consider the specific case of the slip system 111 bar 110 direction. So this is the schematic of the 111 plane, and this is the direction 110 direction. And what is shown here is this Burgess vector here, and we will come to that little later. The Burgess vector corresponding to the displacement of one atom diameter is A by 2 bar 110. So this is A by 2. There is a typo here. This is A by 6 it is written. So it should be A by 2 bar 110. That's a correction. A dislocation with this Burgess vector can dissociate into two partial dislocation. So A by 2 bar 110 can dissociate into A by 6 2 bar 11 plus A by 6 bar 1 2 bar 1. So there should be a plus sign here. That is also a typo. Please let us correct it. Stresses around an edge dislocation either attract or repel another parallel dislocation having the same Burgess vector, depending upon how the two are positioned related to other. Right. This also we will see. There are some you may have consideration on energy, but the orientation also will matter sometimes. We will see that why. So we can check this reaction vectorially, correct, by noting that B1 has the coordinates like this, does equal B2 the coordinates and B3, and that is what is shown here, the dissociation. And whether this dissociation can happen or not is purely decided by the Frank's rule. This is a Frank's rule. We just discussed about the Frank rule in a few minutes back. I was mentioning this idea. So we can just simply verify this, whether this is indeed true. You can just substitute this coordinates into this formula and then see whether really the case. If this is not the, if it is not following this, and this reaction will not happen. So this is another a nice schematic which shows that how the unit dislocation dissociate into partial dislocation. The purpose of me bringing this schematic to you is it gives a very good visual appeal how the partial dislocations are kept in the lattice, in a the dislocated lattice. Usually people just show the Burgess vector dissociation reaction and then be done with it, and very rarely we come across this kind of a pictorial representation, which is, in my opinion, very important to get the grasp of what partial dislocation means. So here extra of plane, and then you know that this is a unit dislocation. But the unit dislocation, which is A, how it splits into two, but still it is how the lattice will look like, a distorted lattice will look like. Okay, so that is very important to note. So because of a small movement in or displacement in the lattice position, how it get distorted locally, and then how this is influencing the rest of the atom's neighbors. Okay, so that is very important, and that decides the the fault zone. Okay, this is a side view. So this gives a very nice idea. So the unit dislocation decomposes into two partial dislocations. So what is that? A by 2, A by 2. Okay. But then these two dislocations, how it influences the interatomic distance in a finite area. So that area is called central fault zone. Okay. Okay. We will see that in another minute, a fault region, stacking fault and so on. So this is very useful for that kind of discussion. Okay, so the full dislocation is represented like this. Half dislocation, for our convenience, we can put it like this, L shape, and this is another reverse L shape. The Burger vector also is half. So this is the same way of representing this, but this is much more elaborate way of representing this. And this hatched region gives a area of fault region, right? Fault region. So this is partial dislocation. Of course, this also happens because only after verifying the Frank rule can be verified, and then that will predict that whether this kind of reaction is feasible or not. So coming close to that kind of an idea, there is another important aspect of these dislocations called stacking faults. So if a single A by 6 112 partial dislocation passes through an FCC crystal, it leaves behind a region in which a sequence of stacking of the close packed 111 planes does not correspond to the normal FCC lattice. So this is exactly shown here, right? Suppose if you just assume that this is a partial dislocation of A by 6, we are not showing that, but this kind of a disturbance it will create. So it will not follow a normal ABC sequence in an FCC unit cell. So this is FCC unit cell. You have A layer, and then you have a B layer, and then you have a C layer. So you have 3 layers, A, B, C, A, B, C. This is an hexagonal close packed unit cell, which has the packing of A layer, B layer, A layer, B layer, and so on. So in a 111 plane view is normally shown like this. So A layer, and then you have an inverted triangle void is B layer. Again, a normal triangle void is C layer. So this is a stacking view, and so what is written here? Suppose if you have this kind of a partial, try to move from here to here. So this is what it is. This is the same partial, A by 6 partial dislocation moves a plane C. So this void to this void. So what is this C void? C void is a equilateral regular triangle void. And from that to it tried to move to that inverted triangle void position. I mean, I'm just giving the description of the void just to indicate the position of the atom. So if it tries to move from this position to this position, then also it creates a packing sequence change. That is, it creates a region where the packing sequence is HCP rather than FCC. So this is another problem. So if you look at the stacking order near a stacking fault in FCC crystal is compared with the stacking in FCC and HCP lattices, and near a twin boundary in FCC crystal. So this is the AB sequence in HCP unit cell or HCP lattice. This is ABC in FCC lattice. Suppose if there is a fault, suppose what we have just moved in the previous slide, the C is moved, then it creates that layer. So this is ABC and then it becomes AC. So this is a region of a stacking fault. The similar way, so it becomes AC, right? So here, similarly, it can also form a twin if it moves like this, ABC and then AC. So here it becomes twin. We will see when we look at the mechanics of twins also, we will refer this. The atom displacement is very, very small but homogeneous. You have to remember that. How the twin, if you can see that, the atom displacement are fraction of interatomic spacing, but it has to happen in a homogeneous manner for large number of atoms. It has to cooperate and form this boundary. We will see that when we discuss the twinning, but here it is considered, here we are concentrating on the stacking fault. The stacking sequence near a stacking fault in an FCC crystal is similar to the packing sequence in HCP lattice. That's known. Because this is not the equilibrium structure of FCC, the stacking fault raises energy. So this we already know. See, here we are still talking about a dislocation only. But here it changes the sequence of the stacking. It becomes a fault. Obviously, that will raises the energy of the system. And the increase of energy depends directly on the area of the fault. So since this is, as I just showed you in the previous slides, it takes quite a bit of a region, faulty region. No, it pushes all the interatomic spacing in the nearby region to some extent. It completely disturbs. So it is considered like a region. So the energy is also measured per area. Okay, the dislocation energy is measured by unit length, but stacking fault, it happens over a region or area. So the here energy per meter square area, right? So that is the only difference between considering individual dislocation and versus a stacking fault region. The stacking fault energy, gamma stacking fault, is the energy per area of the fault and can be regarded as a surface tension pulling the partial dislocations together. Yeah, so this is another nice way of connecting things. So now that we are familiar with what kind of a stress field around the edge dislocations and how it's going to affect, so we can now can easily recognize. So this is two edge dislocation of the same sign. So mutual repulsive force from the each stress field, and this is an attraction caused by the stacking fault. Suppose if you have this kind of a configuration, two partial dislocation A by 6, 1, 1, 2 separated by a stacking fault. So this is a similar figure what I just showed before, but it is much closer look compared to the other one. So two partial dislocations come from both sides, and you can see that this movement from inverted triangle void position to the triangle void position. So in between region will be not a perfect FCC, it will be a region of a faulty region. So this region is called stacking fault region, and the energy associated with this region is called stacking fault energy. Equilibrium spacing between the two partial dislocations correspond to the separation at which the mutual repulsion and attraction balance. So this is something about how these stacking faults are stable. So you know that if the repulsive and attractive forces are in balance, then they are trying to be some stability. So that is all it means. Okay. Now we will slowly move, get into the dislocation motion, right? See, so far we have seen the type of dislocations and dislocation energy, dislocation strain fields, and the detailed description of strain fields and its consequences on the second phase particles or second foreign atom or solid solution, or even with the other dislocations, how it is going to react. And now we will slowly get into the dislocation mechanics. And then the first step is we should describe what is the dislocation motion happens. How does dislocation motion takes place? So here is a nice example here. This is a lattice, 2D lattice with edge dislocation, and the shear stress is applied on this both direction, here and here. And what you are seeing here is have a close look at this, and the atoms are coming, since because of the shear stress, the atoms are trying to move away from this equilibrium position, which is given by the dotted circle around each of the atoms, and this is a slip plane, and we have marked the atom 1, 2, 3, 4 in yellow. Okay. See, we are now trying to give some some atomistic accountability of how dislocation moves. Okay. Please remember that we are still talking about elastic deformation, right? Because the full stress field and energy is described by elasticity theory only so far. So suppose if you look at the atom 1 and its reaction because of this shear stress, what it will do, the shear stress will try to move away from its position, because of the shear stress is moving this direction, right? But at the same time, the atom number 2 and 4 will try to move opposite direction, get into closer to equilibrium position. That means there should be some energy balance. What is the balance here? The energy, elastic strain energy, which is stored in this atom, right? Or when it tried to move, that energy is balanced by this external stress, and the same energy will be equal if the same elastic stored energy which is trying to move from this position, okay, is balanced by this same elastic stored energy to restore this 2 and 4 in its equilibrium position. Then that dislocation will, this atom will try to move. Okay, this is with respect to just motion of atom 1 with respect to 2 and 4, because it both in opposite direction. That means the elastic stored energy responsible for holding that atom 1 in that position and 2 and 4 in their position should be restored or balanced by the application of shear stress. So that is the idea. Otherwise the work to be done by the external shear stress is to give this energy balance. Then the atom will move from that position and if the external stress is good enough to move this to the extreme right, then this crystal will slip. So this is one way of looking at it. Okay, how the dislocation moves. The other important point we have to remember in mind when the dislocation moves, there are two things. The edge dislocation against screw dislocation. There are when the dislocation moves, it moves parallel to the edge dislocation moves parallel to the motion of the dislocation. I mean the dislocation moves along with the dislocation line, the direction of the dislocation line. Okay. On the other hand, it moves perpendicular to the dislocation line. So this is what it is. So this is screw dislocation, right? These are the good schematic shows how the motion of the edge dislocation takes place in a lattice. So you see that the extra half plane is getting shifted from a position A to position B to position beyond D, in fact, and it creates a unit step of slip. So this is something like similar to how the caterpillar moves. So this schematic clearly brings that analogy, how the caterpillar moves. Right? It's again, if you look at the stress field also, it will go like this. If you remember some of the stress field, it's a nice motion like that. And if you look at the other aspect of the motion, suppose if the vacancies are involved in the dislocation motion, then the extra half plane will become shorter. How it becomes shorter? Suppose if the vacancies are getting attracted by this compressive tensile force, or the vacancy moves here, then the atoms will go here, then this will become shorter, right? The extra half plane will become shorter. So that is normally in this situation, the compression strain from both ends will aid this this kind of a mechanism. That's what is shown here. So you should also remember that if this kind of vacancy motion is there, the little bit high temperature later we will see a line of a complete string of vacancies has to form in the dislocation line for the entire half plane to move up. Right? So a huge dislocation vacancies have to migrate to move the extra half plane up. That is another way of looking at the climb motion. Okay, this schematic, very interesting schematic shows, and it kind of, it gives an idea what really happens if the edge dislocation moves in a lattice, and what is the consequence. What is the consequence here? The edge dislocation comes and the A letter is there here, and it cuts through that and on the glide plane, and it makes a shift. So the shift, the measurement will be equivalent to 1 Burger's vector, right? So what does it mean is the relative lattice displacement produced by the glide motion of dislocation leaves a new neighbors of each environment. You may restore the lattice configuration, but each atom will have its new neighbors. That's my idea. Okay. Okay. Another very important slide. This is, we'll spend some time. Suppose now that in gliding along its slip plane, an edge dislocation meets obstacle to its passage. such as a pair of precipitate particles, which are not as easily sheared as is the matrix material. B and C. There are two hard particle which is not shearable. It is an obstacle for the dislocation motion. So this is a dislocation line which encounters these two particles, and it tries to bow. The bowing takes place. And what else is happening? So if you look at this, okay, the geometrical model for the calculation of dislocation line tension. So this line tension word is not new to us. We have already seen it, right? Line energy, we correlated this surface energy to, surface tension to surface energy, and line energy to line tension. We have already discussed, right? So the dislocation line tension brought about when the dislocation encounters obstacle B and C and starts to bulge through the between them. The applied shear stress tau gives a normal force. What is normal force? Tau BL. L is the distance between the two obstacles B and C, and tau B, this is a force, right? We are very familiar with the tau B on the line segment, bowing it out between the pin points. This force is balanced by the parallel component of the dislocation line tension. What is the parallel component of the dislocation line tension? So this is a T. Okay, parallel component is T sine theta. Okay, so this is T. This is T sine theta. So we have 2, so it is 2T sine theta. So tau BL is equal to 2T sine theta. Simple force balance, right? So where L is the distance between B and C, and the replacement of T in the equation by its equivalent from its equation similar terms, what we have already seen, tau is equal to 2GB by L sin theta. This is the shear stress that the dislocation encounters when it meets the two obstacles and non-shearable particles. Okay. So this is very important idea. As I said, this expression will be very useful when we go to the strengthening mechanism aspects. So it may be seen from this equation that increased stress is required to cause increased bowing of the line segment until the segment is semicircular. At this stage, theta is equal to 90, and the stress tau assumes its maximum value. Tau max equal to 2GB by L. Yeah. So this is obvious. At theta 90, you can just plug in this value and see you get this. According to this equation, dislocation which does not meet any obstacle, sin theta is equal to 0, should be capable of moving at a vanishingly small stress. If it does meet obstacles, a higher stress is necessary, the smaller the value of L. So this is also a very important statement. So how the obstacle size and the distance between them influences the stress required for the dislocation to bow or counter this obstacle. It clearly explains. Okay, finally I would like to show one small images about dislocation motion. So this is a screw dislocation which is supposed to move here in the straight line, but then it is going into some other plane. It cross slips, right? It need not screw dislocation always glide. I mean, it need not glide in a same plane, but it will go to the next plane by cross slip mechanism. Okay, and this edge dislocation, McKinsey movement, we have seen it will try to climb. Okay, climb motion. So similar, I mean, there are a lot of mechanisms, or I would say that mechanics of dislocations are also useful to explain the crystalline materials deformation behavior. Right? So we will see a lot more examples of dislocation motion, and then I would say mechanics in much more detail in the next class. We will stop here and see you later. Thank you.